This is my first video in a series of linear algebra videos based on the Sheldon Axler book, Linear Algebra Done Right. In the foreword to his book, Sheldon Axler does mention that his book is meant to be a second course in linear algebra. When I do my videos, I will assume some knowledge of linear algebra, but I also assume that it may have been a while since you've had it, so I will review a few of the steps to get you up to speed. That said, I do have a separate video series called Quick Introduction to Linear Algebra that will get you up to speed in 5 hours or less. It'll give you the main points of linear algebra. One more series I have done on linear algebra for people who are more interested in its applications are based on the book Linear Algebra and Its Applications by David Ley, Stephen Ley, and Judi McDonald. It's an excellent book. All my videos start off with an overview slide, which I try to squeeze in as much as I can that overviews the video. And I do this because it makes me feel better when I see everything on one page because I feel like it's manageable. And second, because I feel like it's a good start for a cheat sheet for any exam, which I'm always looking for when I'm taking a class, or a really good summary of the chapter I'm looking at. So I'm warning you that the start of my video will always open with our overview page, which will be quite dense. Okay, so I guess that's enough of introduction. We're ready to start. In this video, we are going to introduce the definition of a vector space. This is our overview slide, which we'll spend about 5 minutes on before we go over this topic in more detail and with many more examples. We start with the definition of a vector space. That's a set of vectors, sometimes called points, but it's a set of objects. We denote our vector space with a capital V. Then we have a set of objects, which we denote generally with lowercase letters, and I put the bar on top so you can know that this is a vector, not a scalar. So we have a set of vectors along with a way to combine two vectors with an operation called addition, and then a way to multiply a vector by a scalar called scalar multiplication. To be a vector space, the set of vectors along with these two operations of addition and scalar multiplication must satisfy these 9 conditions. The first 2 conditions deal with closure and that we don't escape our set V of vectors. So when you combine 2 vectors with vector addition, your resulting vector must still be in your set V. Similarly, when you do scalar multiplication of a vector times a scalar, your resulting vector must be in the set V. We also have some properties that must hold for our vector addition. First of all, vector addition must be commutative, it must be associative. Also, there must be an additive identity. This is the one requirement for an existence of a certain vector, and that is we must have a vector which we will call the 0 vector or denote with the 0 with the bar over it, and the bar is to distinguish that from the real number 0. So this is the 0 vector must exist in the set V such that any vector plus the 0 vector will give you back the any vector V. We also have an additive inverse. So once you have a vector V, there must exist another vector W that's its inverse, such that V plus W equals 0. There's a scalar multiplicative identity, that is the number 1 or unity, times your vector V must give you back vector V. There's a scalar distributive property, and then also scalar multiplication associativity property. Our canonical example of a vector space and a vector space that you are familiar with from vector calculus or multivariable calculus is Rn. Also Rn, I tend to think of the vector space as an abstraction of Rn along with its vector addition and scalar multiplication. We will consider Rn, and we will look in particular at R2 and R3, which are easier to illustrate. And for R3, we will show that all these 9 properties hold for R3, and I have a couple of the verifications for point 1, point 4, and property 5 here, but we'll do all 9 in this video, in the main part of our video. Then, after we've looked at Rn, we'll consider more examples of vector spaces, including waveforms, polynomials of degree n or less, and the set of functions from a set S to the real numbers. That concludes our overview, so now we can go back and look at all these topics in more detail with more examples, and we'll start with the definition of a vector space. The formal definition of a vector space is that a vector space is a set V of vectors, sometimes called points, along with two operations. The first operation is addition on the vectors, and the second is a scalar multiplication on the vectors. Writing this out, I'm going to say then a vector space is a set of vectors. So here's my set, and I have vectors v1, v2, v3, up to vn. And actually, your set of vectors can be infinitely long. Here I just show n vectors, and I denote them as vectors with this bar over it. So here, for example, I have the vectors u and v. Here I have the vectors v1, v2, v3, up to vn. On these vectors, we have two operators that operate on our vectors. The first is vector addition, and this allows us to combine two vectors. So here I have v1 plus v2, and then the second operator is scalar multiplication. It lets us multiply a scalar times my vector. So here I have vector v1 multiplied by scalar a, and a can either be a real number or maybe it's a complex number. Whether it's real or complex depends on your vector space. So generally we define a vector space either over the real numbers, meaning our scalars are from the real numbers, or we might define a vector space over the complex numbers, meaning our scalars are from the complex numbers. To be a vector space, these operators have to obey certain properties, and these are the properties here that they must obey. First, vector addition is closed. So in other words, when you add two vectors, they still have to be in your set V. You can't jump out of the set. Second, scalar multiplication will be closed. So when you multiply a vector times a scalar, you have to stay in your set V. Third, addition must be commutative. So u plus v must equal to v plus u. Addition is associative. So u plus v plus w, if you do the u plus v first, that should equal to u plus v plus w, where you do the v plus w first. Next, we have an additive identity. So in other words, there exists a vector, which we will call the zero vector, in the set V, such that any vector V in the set V, and our vector space is denoted with this capital V, any vector in V plus the zero vector will give us back our vector V. Next, we have an additive inverse. So for all vectors in V, there exists a W in V such that V plus W is equal to our additive identity. Next, we have scalar multiplicative identity. In other words, there exists this multiplicative identity, which we will call 1, times any vector V in our vector space V will give us back our vector V. We have a scalar distributive property, that is the scalar A times vector u plus v is equal to the scalar A times u plus the scalar A times v. And also A plus B, those are two scalars, times a vector v is equal to A times vector v plus B times vector v. Last, we have scalar multiplication is associative, so A times B, both scalars, times a vector v is equal to A times B times vector v. And the other thing I had mentioned, but I should have mentioned at the beginning, our set of vectors V, or our vector space, is denoted with a capital letter V. And I want to point out, in the book Linear Algebra Done Right, this is how the vector space is defined. Let me enlarge it so we can take a closer look. And you can see the properties here. Maybe I'll move it over here. The properties talk about commutativity of the addition, associativity, goes through down to distributive properties, but it doesn't talk about closure, which is the first two properties I talk about, and that's because the closure is already inherently assumed, because when Sheldon Axler was defining addition on a set, that's the function that assigns an element u plus v in v. So closure is sort of defined as the valid way of doing addition. You have to be closed. So it assigns an element u plus v in v for each pair of elements u, v, and v. And over here for scalar multiplication, when you have the lambda times v, it says you still have to be in your vector space. So closure is inherent in the definition of the addition and scalar multiplication operations. Now that we have a formal definition of our vector space, we're going to look at an example. So our first example is the canonical example of a vector space, which is Rn. And in many ways, this formal definition of a vector space is the abstraction of Rn. And this is the same Rn that you're familiar with from vector calculus. So first, we'll look at Rn, we'll define our vectors, what our vectors look like, as well as our vector addition and scalar multiplication. And then we'll go and show that these operators, the way we define them on Rn, will satisfy these properties here. And just to make things easier, instead of having this infinitely long vector or Rn, we're just going to consider first R3, and then for a few examples, we'll consider R2, just to make it easy for me to draw. We will start with vectors in R3. So we had defined this as a triplet. So x1, x2, x3, you can think of these as coordinates. So you can think of this as an x, y, and z coordinate. And you can also write it in this vector notation, x1, x2, x3. And we say that this is equal to our vector x. I'm going to put the bar over it again to notate that is a vector. And this is should be familiar to you from vector calculus. In vector calculus, we also plotted this. So we would plot R3 with a three-dimensional coordinate system where the first coordinate is the x-axis, the second coordinate is the y-axis, and the third coordinate is the z-axis. So what we would do is we would go out x1 units along the x-axis, and then x2 units along the y-axis. We'll draw our parallelogram. So from x2 drawing parallel to the x-axis, and then from x1 drawing parallel to the y-axis, we have our parallelogram. So this is our point x1, x2 in the xy plane. But now we need to go up x3 units. So from here, we go up x3 units. And I have this notated with this bracket to say we've gone up x3 units. And this is our point x1, x2, x3. Now that I have my vectors defined, I need to define my addition on two vectors. So I have my two vectors here, and because I'm going to draw it for you as well, I went down to R2 instead of R3. So my first vector is x, which is the coordinates x1, x2. My second vector is y with coordinates y1, y2. Now my vector addition is defined component by component. You can also say coordinate by coordinate. But the idea now is vector x plus vector y. We can look at it in this form first. So vector x, which is coordinate x1 and x2, plus coordinate y1, y2, we add our first coordinates together to get the first coordinate of our sum, which is x1 plus y1. And then we add our second coordinates together to get our second coordinate of our sum, x2 plus y2. In column notation, it looks like this. It's kind of nice because we just read across the column and add together. So x1 plus y1, and then x2 plus y2. Next, I'll show you the geometric interpretation. My first vector is the vector 1, 2. My second vector is the vector 1, negative 1. So when I add them, I add the first coordinate together. So 1 plus 1 is 2. And then my second coordinate is going to be 2 minus 1, which is 1. Here I have my vector 1, 2. So I go 1 unit on the x-axis, 2 on the y. My vector 1, negative 1, 1 unit on the x-axis, and then now 1 unit down on the y. So these are my vectors, 1, 2, and 1, negative 1. There are two ways to interpret the vector addition geometrically. The first one is if I'm adding 1, negative 1 to 1, 2, is I take this vector 1, negative 1, I put this origin at the tail end of my first vector. So in other words, moving this vector here so that the origin of my 1, negative 1 vector starts at the tail end of my vector 1, negative 2, now I can draw this vector here from the origin to the endpoint, and this will be my vector 2, 1. And you can see it perfectly aligns with 2 units on the x-axis, 1 unit on the y-axis. The other way to interpret vector addition is you draw a line parallel to your 2 vectors. So we draw a line parallel to 1, negative 1, and we place it at the end of our first vector. Now we have a line parallel to 1, 2, and we place it at the end of our second vector until we have this parallelogram. And the tip of this parallelogram then is our vector 2, 1. The vector addition represents the vector addition. So now that we have vector addition defined, the next thing we need to define is our scalar vector multiplication. So if we have a scalar, here I chose to do alpha for no good reason. Alpha times our vector x, that's alpha times, let's say our vector x is from R2, so x1, x2. We define that as the scalar times the first coordinate, alpha x1, and then the scalar times the second coordinate, alpha x2. So this will be our scalar multiplication. Geometrically, what scalar multiplication does is it will scale our vector, which is why it's called a scalar multiplication. So for example, if our vector is 1, 2, which we have drawn here, and we multiply it by 1/2, that will mean we multiply the first coordinate by 1/2, which gives us 1/2 times 1 is 1/2. The second coordinate multiplied by 1/2, which is 1/2 times 2, gives us 1. And what you can see is that vector, the 1/2, 1, is the same vector as 1, 2, except half as long. Similarly, if we look at the vector 1, negative 1 over here and multiply by 2, algebraically that gives us 2 times 1, which is 2, and 2 times negative 1, which is negative 2, which is the same vector as 1, negative 1, except twice as long. Oops, 2, negative 2. And I should go ahead and label this. This will be my 1/2, 1. With our vectors defined now, our vector addition defined, and our scalar vector multiplication, often just referred to as scalar multiplication defined, we can verify now that our vector addition and scalar multiplication satisfy all of these properties, and therefore our set Rn, along with these 2 operators defined in this way, do indeed form a vector space. And that's the vector space, in this case, well, over here it's for R2. Verifying these 9 properties is sort of a chore because there's 9 things and it's algebraic and not very interesting. But for this first example, I'm going to go through this entire list. And actually, I'm not going to show it for Rn, but I'm going to show this list for R3. So we know what R3 looks like, we know what vector addition looks like, we know what scalar multiplication looks like. So what we want to show, the first condition, which I have copied here, vector addition is closed. So in other words, if we have a vector u and a vector v, that the addition, u plus v, is also in R3. And that's fairly straightforward. So I have my vector v, and I rewrote it in terms of its coordinates, v1, v2, v3. I have my vector u rewritten in terms of its coordinates, u1, u2, u3. So when I add them, u plus v, coordinate by coordinate, I get u1 plus v1, u2 plus v2, and u3 plus v3. And you see what we are left with is a vector in R3. In other words, we haven't somehow reduced down to R2 or we haven't jumped to R4. We are still in R3. And just to kind of give you a sense of what closure is, because sometimes an example of something not closed will be just as informative as something that is closed. So an example of a set that is not closed under an operation, consider the set of integers under the division operator. So I can have 2 integers, 1 and 2, but when I divide 1 by 2 using the division operator, you can see that I've escaped outside of my set of integers. So we would say the set of integers is not closed under division. Whereas here, we want our set of vectors to be closed under our vector addition. And in this case, in R3, R3 is closed under our vector addition. The next property, which I have moved down over here, is scalar multiplication is closed. So for A times a vector u, we'll find that that's also in V. So A times a vector u in V then is equal to, by the definition of scalar multiple, this scalar times each of these coordinates. So AU1, AU2, AU3. And we see this is still a vector in R3. Our next property is addition is commutative. So when I add the vector u to a vector v, that's equal to the vector v plus the vector u. So here I have my vector u, which is u1, u2, u3, and my vector v, which is v1, v2, v3. Using the definition of vector addition, component by component addition, I get u1 plus v1, u2 plus v2, and u3 plus v3. Now, the u1s, u2s, u3s, and the v1, v2, v3, these are all real numbers, and the addition of real numbers is commutative. So I can switch the order of these, and I get v1 plus u1, v2 plus u2, v3 plus v3. And now using the definition of vector addition kind of backwards, I can separate out my two vectors where I have v plus u then. The next property, which I've moved over here, addition is associative. So u plus v, if we add those two vectors first and then add w, that's going to be equal to adding v and w together first and then adding u. So here I have u plus v added together first and then vector w. So adding u plus v from definition of vector addition, that's u1 plus v1, u2 plus v2, u3 plus v3, plus our vector w. Now you notice now our components or our coordinates u1 and v1, those are just real numbers, or maybe they're complex. But let's just say they're real. Oh, actually we're in R3, so they're just real numbers. u2 and v2, these are just real numbers. So here we have a new vector and our vector w. So now we can add these two vectors. So we get u1 plus v1 plus then our w1. Adding the second coordinates, we get u2 plus v2 plus w2. And then finally, u3 plus v3 equals w3. And again, from here to here, that's just the definition of vector addition. But now, again, u1, v1, w1, these are just real numbers, and real numbers are associative. So I can add these two numbers first. So our u1 plus v1 plus w1 is equal to u1 plus our parentheses v1 plus w1. Similarly, for the second and third coordinates, again, we do that. We can do this because the addition of these real numbers is associative. Finally, using the definition of vector addition backwards, this here is one vector, our v plus w vector, and this here is our u vector. So what we have shown that adding u plus v first and then adding w afterwards is the same thing as adding v plus w first and then adding u afterwards. The next property is the additive identity. So there exists a zero vector in the set V such that any vector V plus 0 is equal to V for all vectors V in the set V. So we consider, for R3, we consider the vector 0, 0, 0. Then we add it to any vector V plus 0, and you'll see by vector addition, this is v1 plus 0, v2 plus 0, v3 plus 0. These are just real numbers, so that gives us back our original vector v. Our next property is additive inverses. So for all vectors v in the set V, there exists a vector w in V such that the vector v plus the vector w equals our 0 vector. So given a vector v, which I have written as v1, v2, v3, let's consider negative 1, our scalar negative 1, times v, which is equal to negative v1, negative v2, negative v3. This vector here is going to be our additive inverse, or what this in this line is considered w. So when we add v plus our additive inverse, our negative v1, negative v2, negative v3, we do component by component addition, so v1 minus v1, v2 minus v2, v3 minus v3, so we get back the zero vector, or the additive identity that we found in step 5. Our next property is the scalar multiplicative identity, which says there's a scalar, which we'll call unity, denoted with 1, times any vector v in our vector space will give us back our original vector v. So our scalar 1 times v1, v2, v3, so 1 times, using our definition of scalar multiplication, 1 times each of the coordinates gives us 1 times v1, 1 times v2, 1 times v3, and that's simply equal to v1, v2, v3. So 1 is our multiplicative identity. Next is our scalar distributive property. So a scalar a times vector u plus v is going to equal to the scalar a times the vector u plus scalar a times the vector v. So here I have a times the vector u plus v, which is equal to adding u plus v, gives us a times u1 plus v1, u2 plus v2, u3 plus v3. Again, this is just from adding the two vectors, our vector addition of u and v. And now, by definition of our scalar multiplication, we just multiply our scalar times each of the coordinates. So this is a times u1 plus v1, a times u2 plus v2, a times u3 plus v3. Again, from this step to this step, that's the definition of our scalar multiplication. Now, a, u1, and v1 are all real numbers. And there's a distributive property of real numbers where we multiply this here, a times u1 plus v1 is equal to a times u1 plus a times v1. So I've written that here. Again, using just the distributive property of real numbers, a times u2 plus a times v2. And finally, we have a times u3 plus a times v3. Next, by definition of vector addition, we can separate out this vector here from this vector. So we have a u1, a u2, a u3, plus the vector a v1, a v2, a v3. And then finally, using the definition of scalar multiplication, that's what this x is, multiplication, we can factor out our scalar a. So this is vector a times u plus a times v. And I know I said I would do all of these steps. There is a second part of this step which I'm going to skip, but it's the scalar a plus v times the vector v will be equal to the scalar a times the vector v plus the scalar b times the vector v. But this proof is very similar to this one here, and you'll notice that all these kind of algebraic properties, this addition is commutative, associative, again, the distributive properties then, these all depend on using the vector addition and scalar definition of scalar multiplication, and then using the properties of real numbers, because these a's and u1s and v1s, these are all real numbers. My last property is that scalar multiplication is associative. So if I have two scalars multiplied together times a vector v, that's equal to my second scalar times my vector multiplied, and then afterwards multiplied by scalar a. So if we look at our scalar ab times our vector v, which is v1, v2, v3, by the definition of scalar multiplication, well, the multiplication of two scalars is just a real number, another scalar. So we can multiply that by each component, each coordinate of our vector. So we have ab v1, ab v2, and ab v3. Now, because the a, b, and the v1, v2, v3 are all real numbers, and multiplication of real numbers is associative, I can switch the parentheses or move the parentheses so that I have a times bv1, a times bv2, and a times bv3. Finally, using the definition of scalar multiplication, I can factor out my scalar a, and then I have my vector b, v1, bv2, bv3. So this is just my bv vector times my scalar a. So we just finished showing that the space of vectors in R3 with vector addition and scalar multiplication as defined as we did in vector calculus is a vector space. And this is true for any Rn, so we could do R2, we could do R4, and any field, so it doesn't have to just be real numbers, it could be complex numbers to the n, Fn. Our next example of vector space are waveforms, and waveforms are in so many natural phenomena such as light waves, audio waves, waves on the water, waves on a drum head. So actually I guess that would be an audio wave. But anyway, we need to first define then the vectors along with vector addition and scalar multiplication. So our actual waveform will be our vectors. So here's a sine wave. Here's our sine x plus sine 2x wave in green. And then in yellow, we have the sine 2x wave. So those three waveforms are three examples of vectors. Now we need to define our vector addition and scalar multiplication. Vector addition is just our wave superposition principle that we have from physics. And we'll illustrate that with our blue wave, the sine x, plus our yellow wave, the sine 2x. When we add them together, we get this green wave, the sine x plus sine 2x. And the way we do that is for every value of x. So let's take one value of x over here. Let's take an easy one. This here where we have everything crossing at 0. So for this value of x right here, the blue wave is 0. The yellow wave is at 0. So when we add the two zeros together, the two heights of 0 together, we have the green wave is also equal to 0. Let's take another value of x, maybe this value over here where the green is sort of at a peak. At this value of x, the blue wave is approximately 1, and this yellow wave is maybe 1.3 or something, 1 1/3. So we expect the green wave to be 1 plus 1 1/3, so somewhere around 2 1/3. So here's 2, approximately 2 1/3. And then we can go point by point again. Here's another 0 over here. Here we have, let's take one more point over here along this line. For this value of x, the blue wave is here at -1. The yellow wave is a little over 1, so we expect the green wave to be a little over 1, which it is. Next, we need to define our scalar multiplication. So a scalar times our wave essentially takes the height of our wave and at each point multiplies it times the scalar. So for example, here we have in blue the sine wave. And when we multiply 2 times sine x, we go through each point on the sine wave and double its height. So here, the sine wave's at 0, so when we double it, we still get 0. Here the height is approximately 1, so when we double it, we're going to get height approximately 2. Here our height is approximately -1, so our height will be approximately -1. And you can see that if I had done a good drawing, the height of 2 sine of x is twice the height of sine of x at every point. Looking at our properties, you can probably convince yourself that vector addition is closed. When you add two waves, you're still going to have a wave. And scalar multiplication is also closed, so adjusting the height of a wave still gives you a wave. For addition is commutative, we're going to hand wave that a little bit, but you can kind of intuitively see that addition is going to be commutative because we're doing point-by-point addition because of the superposition principle. So essentially, we're just adding the height, or a real number then, plus another height, which is another real number. And since the addition of real numbers is commutative, we assume it's going to carry over in our superposition. So here our green wave, our sine x plus sine 2x, we're going to expect that that will equal to sine of 2x plus sine of x. So again, I'm not going to formally write out all the steps, but that's kind of my hand wave. Associativity is similar. For the additive identity, that's just going to be the 0 wave, which is kind of funny to draw because it looks like I'm just tracing the axis, the 0 axis, but that's exactly it. So this black line here is my 0 wave. When I add it to my sine function, I just get back sine. The additive inverse then is kind of the reflection of our waveform across the x-axis. So if this is our sine of x, the minus sine of x, which is this reflection of sine of x, will be our additive inverse, because point by point, when we add these 2 points together, we're going to get down to the additive identity, or the 0. The scalar multiplicative identity, so the scalar, when you multiply it times any wave, the scalar is just going to be 1. Right? When you multiply 1 times sine of x, you get back sine of x. And these distributive properties, again, you kind of expect those to follow from the fact that you're doing point by point, or the superposition of waves will essentially get you down to real numbers. And then the distributive properties or multiplicative properties of the real numbers will then apply and give you these last 2 properties. And the implication of this is, because waveforms are vector spaces, anything that you can consider a waveform, then you can apply all of linear algebra to those waveforms. Remember when I told you Rn was our canonical example of a vector space? So you can consider this definition of a vector space as the abstraction of the properties of Rn. So anything that is a vector space has a relationship with Rn. It's a homomorphic, or it's essentially the same thing as Rn, or can be represented as Rn. But since this vector space is an abstraction of Rn, what we do in linear algebra is we study vector spaces as an abstraction rather than studying waveforms, which is a whole topic in itself. E&M, electricity, magnetism, waveforms, all of that, they're whole semesters of physics. So rather than studying a whole semester of physics and then talking about all these properties or techniques that you can do with them that are basically from vector spaces, what you do is you abstract your ideas from vector space, study your vector spaces, and then later, anything you happen to realize is a vector space, then you just say, oh, well then everything we learned in linear algebra applies. So one of the big things about vector spaces is being able to recognize you have a vector space. So here we're saying that waveforms are a vector space. And when I was in college, we had a professor who had discovered a vector space, and that was a big claim to fame. He was very young. He probably did lots of other things since then, but that was a big deal. And it's a big deal because just imagine you're in some domain working on some problem, and then all of a sudden you realize it's a vector space. Well, now you can bring all of linear algebra and all the tools of linear algebra into your work. We'll do some more examples of vector spaces now. The simplest example of a vector space contains only one vector, and that's the 0 vector. We have to have a 0 vector because that's a requirement right over here. Where is that? The additive identity, point number 5. We have to have an additive identity. The 0 vector exists in the set V. From there, vector addition is closed. There's only one vector in your set, so 0 plus 0 is still 0. Scalar multiplication is closed. Any scalar you choose in your field, so 3. 3 times 0 is still 0, so scalar multiplication is closed. Addition is commutative, whether you add 0 plus 0 or 0 plus 0, they're still both equal to 0. It's associative, we have the additive identity. The additive inverse, 0 is its own additive inverse because 0 plus 0 is equal to 0. Scalar multiplicative identity, 1 times 0 is still 0. Scalar distribution and the scalar multiplication is associative, I'll leave that to you, but scalar times 0, 0 plus 0, you're just going to get 0. So this is the smallest vector space you can have, and you can see that the 0 vector, along with vector addition, our normal vector addition, and scalar multiplication that we defined for Rn, will give us a vector space. Our next example of a vector field is Fs. This is F standing for a field. So this can be replaced with real numbers or complex numbers. And this is the set of functions from a set S to our vector field. For our example, we're just going to say our vector field are the real numbers. So our vectors are functions, right? Our vectors are functions that map from a set S to the real number line. So here I have kind of an illustration. Here I have a set S that has two elements, the number 1 and the number 2, and then f of x will map the number 1 to some real number, and it'll map the number 2 to some other real number. And now the thing about fs is this is the set of functions. In other words, I could map the number 1 to the number 0 and the number 2 to 3.14, and that would represent one function from S to the real number line. But fs is the set of all the functions from S to the real number line. So I need to first map the number 1 to all possible values on the real number line. Of course, that would be infinite. I would map the number 2 to all possible values on the real number line, and then the combination of all those mappings of 1 combined with all the different mappings of 2 would be the set of functions from S to F. So it's not just one example of a function, but all the functions that are possible from S to R. Now I can define my vector addition. Again, my vectors are functions, so I need to know how to add two functions, f and g. So say g is a function from S to R. So then f plus g of x, we're going to use our normal function addition. That will be f of x plus g of x. And our scalar multiplication, so a scalar a times our function f of x will be a times f of x. I'm going to give you an example of an f and g so we can kind of see why vector addition and scalar multiplication will be closed. So I have a function f that maps the number 1 from S to the number 2 on the real number line, and f maps 2 from S also to a number 2/3 on the real number line. Similarly, I've defined a function g. First, it maps the number 1 to the number 1/2 on the real number line, and it maps this element 2 to the number 0 on the real number line. My vector addition then, if I do f plus g of 1, that would be f of 1 plus g of 1, so that's going to be 2 plus 1/2. And also for my scalar multiplication, if I multiply by a scalar such as 2 times f of 1, that will be then 2 times 2, which is 4. So the first thing then I'm going to say about closure of addition is that there are infinitely many functions, and I'll just call those functions h, that map from S to the real number line such that h of 1 is equal to 2 1/2. The reason why there are infinitely many is because now that we've mapped h of 1, h also has to map the number 2, and there are infinitely many ways to do that. So the infinite number of ways to map 2, and then we map h of 1 to 2 1/2. That is what tells us that this f plus g, for this example where f plus g maps 1 to 2 1/2, is closed when we add the two functions f and g of 1. When we plug in 1, that we will have, it'll be closed under this s mapping to r, or f of s, where f is the real number line. Similarly, for 2 times f of 1 for scalar multiplication, that's equal to 4. So we have some function h that's going to map the number 1 to 4, and then there's an infinite number of ways to map our 2. So there's an infinite number of functions that satisfy this one condition. So we have this closure of our set f of s, in this case where f is equal to r. And so I'm not going to actually prove this closure of addition and scalar multiplication because that would be a little bit involved because of the infinite number of possibilities. But this is the example I'm going to give you a feel what is involved with the closure of addition and scalar multiplication. We can talk about the additive identity over here, property number 5. So the additive identity, I'll just call that function capital I for identity of x is equal to 0. You can see that when you add f plus I, you'll always get back f of x. And then the additive inverse, if you're given a function f of x, then multiplying the result of f of x by -1 will give you the additive inverse for f of x. Our next example is the set of polynomials of third degree or less. They will form a vector space. Our vectors then are polynomials of the form px equals ax cubed plus bx squared plus cx plus d. And for this example, we're going to assume that our a, b, c, d coefficients are all real numbers. Then our vector addition, we're going to define it as our regular addition of polynomials. So if you have a polynomial p of x, which is equal to a1 x cubed plus b1 x squared plus c1 x plus d1, so I put the coefficient, or no, I put the little indices 1 for our first polynomial, and then for our second polynomial, our coefficients have the indices 2. So a2x cubed plus b2x squared plus c2x plus d2. So when we add p plus q, our first coefficient for the x cubed term will be a1 plus a2. Our coefficient for the x squared term will be b1 plus b2. Our coefficient for the x term is c1 plus c2. And our final constant is d1 plus d2. Our scalar multiplication is defined just as we would for polynomials. So alpha being a real number or a scalar, times px is equal to alpha times our polynomial ax cubed plus bx squared plus cx plus d, which will be equal to then alpha a times x cubed, alpha b times x squared, alpha c times x, and alpha d as our final constant. You can see that vector addition and scalar multiplication are both closed, satisfying these first two conditions, because when we add two polynomials of degree 3 or less, we're never going to get a polynomial of degree 4, for example. It's always going to be 3, and again, the key here is 3 or less. So it's possible we have a polynomial of degree 2, but that's okay. Scalar multiplication, similarly, when we multiply by a scalar, we're still going to be end up with a polynomial of degree 3 or less. We're not going to do all the rest of these, but we'll do a couple of the conditions. So first, to show that addition is commutative, we need to show that a polynomial u plus a polynomial v is equal to the polynomial v plus the polynomial u. And for this, I'm going to use the two polynomials p of x and q of x because I have them written up here. So we'll start with p plus q, and I'm just going to move this line over here. I started by swapping my coefficients a1 and a2, b2 and b1, c2 and c1, and d1 and d2. Actually, this step wasn't necessary, but I started this way, so here it is. But the important thing now is you're going to start multiplying out, right? These are constants or real numbers. Here, these are variables, so you use your regular algebra. So you have a2 times x3, a1 plus x3, b2 times x2, b1 times x2, c2 times x, c1 times x, and then d2 plus d1. Now I can group according to whether we're p or q, and the p polynomial has the coefficients with the 1 subscript, q has the coefficients with the 2 subscripts. So looking here, grouping together the ones with the 2 subscripts, I have an a2x cubed, I have a, where's another a2, b2x squared, a c2x, and a d2. So those are my first grouping, and then I can group my x1 coefficients over here, which gives me, this here is q of x, and this is p of x. So I have shown that p of x plus q of x is equal to q of x plus p of x, so our addition is commutative. You could do something similar for associativity, the additive identity. We will consider for the additive identity the zero polynomial. That is, let's just label it I for identity equals 0. If you want to make it look more like a polynomial of degree 3 or less, if it makes you feel better, you can write it as 0x cubed plus 0x squared plus 0x plus 0. Then for any other polynomial, p of x plus I is just going to give you back p of x. The next thing we'll look at is additive inverse. Given a polynomial p of x equals ax cubed plus bx squared plus cx plus d, the additive inverse then will be the -1 scalar times p of x, or in other words, minus ax cubed minus bx squared minus cx minus d. We can verify that p of x plus the inverse minus p of x will give us the zero vector. The scalar multiplicative identity is just the scalar 1. You can verify these other two, scalar distributive properties and scalar multiplication as associative property, just using algebra. We've come to the end of our video, but we'll review what we have discussed. We first defined a vector space, which is a set of vectors along with an operation of addition on the vectors and an operation of scalar multiplication on the vectors. And the set of vectors along with its two operations have these 9 properties. First, vector addition is closed. So if you take two vectors from your set of vectors V and you add them together, the resulting vectors still must be in V. There's a scalar multiplication. So if you take a vector U in your vector space V, in your set V, and you multiply by a scalar, then that resulting vector must still be in V. Also, our addition is commutative, so when you add two vectors, it doesn't matter which vector comes first. Addition is associative, so it follows when you add U and V first and then add W, it'll be equal to adding V and W first and then adding U. There's an additive identity, so this is the one existence that guarantees there's at least one element in your vector space. Your vector space must have this zero vector, which we designate with a 0 and a bar on top, and the bar distinguishes it from the scalar or the real number 0. So the 0 vector must be in your set V, and the 0 vector must have the property that when you add it to any other vector, you get your any other vector back. There's an additive inverse. So if you have a vector V in your set V, then there must be a corresponding vector W such that V plus W gives you back your additive identity. You have a scalar multiplicative identity, that's the 1 times your vector V gives you back V. Your scalar distributive properties, and then your scalar multiplication property that is associative. The canonical example of a vector space is Rn. This is the space you should be familiar with from vector calculus or maybe earlier linear algebra courses. And we took a closer look at R3, and we showed that R3, along with the vector addition and scalar multiplication that we define in our video, but also it's the same one you learned in vector calc, also known as multivariable calculus. So we showed that R3 was indeed a vector space. Here are kind of the outlines of our proof for property 1, property 4, and property 5. But we did go through all 9 properties in the main part of our video. We also then looked at more examples of vector spaces, including waveforms, polynomials of degree n or less, as well as a set of functions from a set S to the real numbers. So that's it for this video. Thank you for watching.